All right, hey everybody, this video is going to start digging into exponential functions and look specifically at a real-world problem for exponential functions. This first part will essentially be a review, just kind of the basics of what an exponential function is, and then getting into a very specific problem that you have seen before, but we'll look at it in terms of a little bit more detail and give a little bit more background economically and financially. Uh, and it'll be hopefully fairly interesting. Okay, and so to start, exponential functions play an important role in many real-world applications. Again, we're going to focus on a financial one here in this problem, but it is used in a ton of social sciences. Now, exponential functions, they are the function that is defined by f of x is equal to b to the x. All right, now in these kind of problems, b is a constant, and x is my variable, and notice how that's the power in an exponential function. And so this is called an exponential function with base b and exponent x. And the x, because that's my variable, then what this is essentially doing is an exponential function represents repeated multiplication, essentially whatever x is, so an x number of times. And so this is what an exponential function again represents. It's repeated multiplication, so you are doubling over and over and over, you are tripling something, or maybe you are halving something over and over and over. And so graphically speaking, when we talk about exponential functions, there's two different ways, or two different functions, or not two different functions, there are two different graphs that you could see from an exponential function. One is an exponential function could look like this. This is when b is greater than 1. Typically, applications of this are when you have exponential growth, so population, bacteria, investments, if we're doing interest, and things like that. There is also another way that this graph can look, which is like so. And this is essentially when b is less than 1, and this helps represent decay. So if you ever want to think about half-life, if you want to talk about infectious populations and looking at rapid decay there, and exponential decay. And both of these scenarios are modeled by exponential functions. And when we do this, notice that essentially, again, we talked about this, the base has to be greater than 0, and the base can't be 1 for it to follow suit. Again, if b is greater than 1, this is help to modeling growth. If b is less than 1, that's decay. All right, and so there's a couple of properties here that I kind of want to point out and look at. One of those properties is this, that the domain, what you're allowed to plug in for x and use, is all real numbers. So x can be anything from negative infinity to infinity. The range, so in terms of the floor to ceiling, as far as my outputs are concerned, goes from 0 to infinity. We can see this in both of the graphs, where the graph lands essentially on the x-axis, which is represented by 0, but then the graph continues to go as high as it ever wants to, and we represent that by the infinity. This is the same thing, even if b is less than 1. This graph rises all the way to infinity, but falls down to 0 and never touches it. In both of these cases, when we're dealing with just the basic exponential function b to the x, these graphs will always pass through 0, 1. And this makes sense because if you plug in 0, anything to the 0 is always 1. It doesn't matter what that base is, especially under these constraints for b. This fourth property here is that the exponential functions are continuous, so there's no breaks. We talked about discontinuities before this home learning began. Essentially that there are no vertical asymptotes, there's no holes, there's no jumps, there's no breaks. I can continuously draw an exponential function from left to right, essentially from negative infinity to infinity, without ever having to pick up my pencil. All right, and then as we talked about earlier, and this kind of makes sense hopefully, is that if b is greater than 1, then an exponential function is always increasing from left to right, which is what the negative infinity to infinity is referring to. If b is less than 1, then my exponential function is always decreasing from negative infinity to infinity, meaning, again, we're always falling from left to right when b is less than 1, or we're always increasing from left to right if b is greater than 1. All right, and so this is kind of the basics for exponential functions. You saw this a lot in pre-calculus and algebra 2. And now I want to look at this is a topic specifically looked at in pre-cal, and I just kind of want to review it again. And it's the topic concerning a unique base for an exponential function, and this is called the base of e, which is known as the natural number. And so to start our investigation for e, what we actually do is we look at this kind of weird expression, 1 plus 1 over m to the m. Now, as you'll notice in terms of my note here, we'll actually see this again in the next section. So it's a really important expression that actually defines exponentials, and especially in terms of growth. And if you had me for pre-calculus, we actually looked at this in terms of interest, actually in terms of bacterial growth, in terms of the problem. But for now, let's just kind of focus on this expression here, 1 plus 1 over m to the m. And my plan is to let m go to infinity. In other words, if I continuously plug in larger and larger and larger values for m, what happens to the expression 1 plus 1 over m to the m? In other words, where would it go? Does it approach a specific value? Does it just go off to infinity like we saw before with exponential functions? Does it approach anything unique? And hint, hint, like it will, otherwise we wouldn't look at it. And so I've got a table here that you could go through and complete. So if you want to kind of explore on your own what this function does as m gets bigger, essentially go through and plug 10 in for m, then plug in 100, then 1,000, then 10,000, etc. Going through and filling out this table. I'm going to pause for a second so you can pause the video, but I will then go in and calculate these so that way you'll have values for them. Okay, so I'm going to just get my calculator out. All right, and so I'm just going to go through and compute. So I'm going to plug 10 in. So essentially I'm plugging in 1 over 10 to the 10th power here. So 1 plus 1 over 10, excuse me, to the 10. I get then 2.59374. Now I'm going to go through and plug in 100. So I've got 1 plus 1 over 100 to the 100. I get 2.70481. I'll go one more, 4, just around. And something I want you to notice here, at least just to start, is that going in between these two numbers, the 1's decimal place here, this first digit, has now become essentially fixed. So it'll always be 2 point. All right, so let's go through and do 1,000. And I'll kind of speak on that a little bit more. So I have 1 plus 1 over 1,000 to the 1,000th power. And I get 2.7, see, I'm going to stay consistent, 2.7169, 2, and then I'll round that through to a 4. And so notice going into 1,000, when I go to the next step, if I compare these two values here, they both have a 2.7 in common. So we've gone 2.593 blah, blah, blah to 2.704. So they have the first 2's in common. The next answer was 2.716 blah, blah, blah. So 2.7 is in common. If I increase and go to 10,000, then my expectation is that I'm going to get another digit fixed. And so you'll see that when you do 10,000, you'll get 2.71846. In other words, again, notice how now 2.71 becomes fixed. So we're slowly getting more and more decimal places set. as I increase the values. So I'm going to do 100,000 now. So 1 plus 1 over 100,000. I get 2.7. So let me get my blue back. 2.718,268. And again, comparing previously now, 2.718 seems to be fixed in place now. And then finally, let's plug in 1 million. And I get 2.718. 2.718. It's a terrible 8. 182804 or 05 if you want to get another decimal place there. And so notice now that the numbers they have in common are 2.7182. And then if we went again, we'd probably find that the 8 would be fixed, etc. So this is where I'm actually going to finish in terms of looking at it, because by now we've made it to the 10, 100,000th, 10,000th, 100,000th place. And so our conclusion then is that as m increases without bound, aka we're letting m go to infinity, then what we're seeing is that this expression for 1 plus 1 over m to the m starts to approach this very special and unique value where these decimal places continue just to become fixed. And how I kind of picture this, just to kind of give hopefully a better explanation of what's going on, is I like to imagine you've essentially got a wheel of digits. If you think about like a bike lock, that's got a bunch of little rotating sections here with numbers on them. And we're essentially trying to find the right code to open it. And what's happening is these things will spin until they hit the right number. And then the next digit will spin until we hit the right number. Then the next digit will spin. And as we keep going and going and going, these values will get fixed, like we're seeing here. And we start hitting this very specific decimal point that seems completely random in terms of numbers. But what's really important to get from this is that as this is increasing, this number is always going to appear. And so we call this E. If you were to take your calculator in mine, my E is second ln. So in the calculator, if you do second ln and you get E, do E to the first power, and what you should get is 2.71828 with the remaining decimal places. Again, meaning that E is representing this decimal number that essentially represents continuous growth or continuous decay. And this is why it's referred to as the natural number, because in nature, things aren't just waiting until the chime of an hour, or, they're sitting and looking at a clock and saying, okay, we're going to multiply right now. Now we're going to multiply now, right? And say every 60 seconds, we're going to split, right? It's a continuous splitting, continuous growth, continuous decay as things are happening in nature. And that's why, again, this is called the natural number, because if I want to model that type of growth and decay, I choose my base of my exponential to be E. In other words, I let B be E, which is approximately 2.71828. And when I do that, my exponential function becomes e to the x, and this is known as the natural exponential function. Now, really, all you need to really kind of take away from this again is that this is still an exponential function. So all of the properties that we just looked at still apply here, right? The domain for the natural exponential is all real numbers. The range for the natural exponential is 0 to infinity. It's continuous from negative infinity to infinity. It'll pass through 0, 1, because e to the 0 is just 2.718 to the 0. That's 1. and because this is greater than 1, then e to the x is always increasing from negative infinity to infinity. So its graph, if you were to graph this on your calculator or in Desmos, would look something like this, or again, this would be 0, 1 as a basic power function. Now, this function is, again, very, very important, and we're going to see this a little bit later when we're dealing with this idea of continuous growth or continuous decay. All right, and so the next section we're going to look at our real-world problem. There's roughly going to be about 3 parts to this real-world problem, really just kind of defining financially a couple of important terms. So it's a little bit longer than you may be used to. It's also going to dive a little bit more in depth into the real-world problem, which is compound interest. All right, so now in this section, we're going to start looking at compound interest, which is a natural application of exponential functions, specifically in economics and in finances, as I talked about at the end of the previous section. All right, now before we get into compound interest, though, we're going to start with the foundation, which is looking at simple interest and kind of recalling what this is referring to. Simple interest is specifically interest that is computed only on the original principal. Thus, if we let I, capital I here, denote the interest on a principal P, and principal is whatever starting amount you have, at an interest rate of R per year for T years, then we can calculate the amount of interest as my starting amount, whatever that principal is, times the interest rate. So what percentage are we going to get per year? And then multiply it by the number of years. And this is going to calculate how much extra money we're going to get on that starting amount. And so this again, as though is just the interest that we're going to get. So this is just the extra money. So if we wanted to know how much would actually be in our account at the end of this set time, whatever T years is, then what we're looking at is what's known as the accumulated amount, which you'll see in the second sentence here, which we're going to denote using the capital letter A. And so this is specifically the sum of the principal and interest after T years. And so then A would be equal to whatever amount we started with plus the amount we've earned in interest. Well, we know what I is because of our previous line here. We know that interest is PRT. And mathematically, to make this expression a little bit easier to work with, notice how both of these terms have a P in it. And so I'm going to factor that P to the front, leaving me with a 1 plus RT remaining. And this is my simple interest formula. This is the formula that we're going to be using essentially for the remainder of this section. So this will calculate the simple interest accumulated throughout. So we're going to come back to this a lot here. All right, but this is now just simple interest. Now, frequently, depending on the accounts and things that you're looking at, interest is actually calculated according to what's called compound interest. And compound interest, again, is something that you should be semi-familiar with. And you'll see that essentially defined here in the second line. The idea and why compound interest is so nice is that interest is actually earned periodically, and this interest as it's earned is added to your principal, and then interest is calculated again. So you're essentially making interest on interest on interest on interest, and so the percent is being repeatedly multiplied. Thus, compound interest is such a good example for exponentials, because you continuously get this percentage of multiplication that continues to add on itself and add on itself and add on itself, which is better than just calculating a flat, simple interest that's added over time. Multiplication, always better than addition when it comes down to it. And so what we're going to do is to essentially come up with the compound interest formula we're going to use this example here to go through and kind of see with numbers the formula and through some analysis come up with the main idea. So let's suppose that we have $1,000 in principal. So my P is $1,000. And let's say it's deposited in a bank for a term of 3 years. So my overall T is going to be 3. That's my goal here. And I'm earning an interest at the rate of 8% per year. So my R in this case is going to be 0.08, representing the 8%. Now, you'll notice this is talked about in terms of nominal or its stated rate. And we'll talk about this more in the next part. And this is going to be compounded annually. So at the end of a year, we will calculate interest, and then interest at the end of the second year will use what we have in the first to calculate, and vice versa, or not vice versa, but continuously going on and on and on. And so let's kind of look at it and break it down that way. So after the first year, let's calculate how much has been accumulated. So I want to find A1. Well, excuse me. A1 is calculated by doing my principal amount times 1 plus RT, which is the amount of time that's surpassed. Now for A1, my principal is 1,000, 1 plus my interest rate, which is 0.08, but the time that's passed right now is just 1 year. Excuse me. And so that's just going to be 1, and so this is going to be 1,000 times 1.08, which comes out to be 1080 or $1,080. So that's how much I'll have in the account after the first year. Now, after the second year, the accumulated amount is going to be calculated by what we started with and at the end of the first year times 1 plus my interest rate, which is 0.08. And the time that's been accumulated now is still 1 year because we're essentially going 1 year time again. Well, from A1, we essentially have A1 was 1,000 times 1.08. Well, notice that I'm ultimately going to be multiplying another 1.08. So this is 1,000 times 1.08 squared, which is approximately, let me get my calculator out. Gotta get to it. 1,000 times 1.08 squared. I get $1,166.40. So at the end of the second year, that's how much would be in my account. All right, well, let's figure out what would be at the end of the third year and the final year. So A3, this would be calculated based on my final amount, which is in A2. And then I'm going to multiply this by 1 plus my interest rate, which is 0.08, times 1, because that's how much time has elapsed between the second year and third year. Well, A2 again was 1,000 times 1.08 squared. Notice that we're going to be multiplying another 1.08. So this is 1,000 times 1.08 to the third, which comes out to be, plugging this in the calculator, approximately $1,259.71. So at the end of the third year, a deposit of $1,000 with an interest rate of 8% compounded annually, I would have $1,259, roughly $1,260 accumulated in the account. All right, now This was going through and using a lot of the numbers. So let's go through and actually kind of analyze what we have. All right, so I'm going to move this up a little bit so we can see it. Okay, so at the end of the first year, notice we calculated this by essentially doing my initial principal times 1 plus R T, which was again 1,001 plus 0.08 because time was only 1 year. When I did it again, this came out to be the A1 times 1 plus 0.08, which was just 1,000 times 1 plus 0.08 times 1 plus 0.08. And then in A3, this was A2 times 1 plus 0.08. Well, that's 1,000, 1 plus 0.08 squared times 1 plus 0.08. And this one here was P 1 plus R. The second one now notice is P 1 plus R squared. And the third one is P times 1 plus R to the third. In other words, it looks like that if I wanted to continue doing this, I essentially am finding a general pattern, and it suggests that that pattern is for t years, the accumulated amount would be P times 1 plus R to the t. And so this would be my compound interest specifically if I was going to compound it annually. And you can look at the wording as far as this goes. The accumulated amount if P dollars are invested over a term of T years, earning interest at a rate of R per year, specifically compounded annually, I could follow this formula. And so we could actually jump straight down to this in the previous example, and we should get 1259.71 when we plug in our respective values. All right, now, this is though only compounded annually, meaning we're only actually calculating the interest once per year, adding that in, and then doing the next calculation. A lot of companies actually compound more frequently than just annually. You could see quarterly, semi-annually, monthly, daily, and those values again, 365, etc. And so there's a couple more terminology, and this is going to be a little bit different than what you may have seen in previous classes. That interval of time between successive interest calculations is called the conversion period. And so this is essentially that period. So beforehand it was annually. If you compound compound quarterly, then your conversion period would be 4. If you compound daily, then your conversion period would be 365. All right, and so if we generalize this, so if interest at a nominal rate of R per year is compounded n times, then the interest rate per conversion period is a little bit different. The way that it would be calculated is I'll call it a lowercase I. It would be equal to that annual rate divided by the number of times I'm compounded, because this R here is the annual interest rate. It's the rate that I'm making over the course of the entire year. And this is going to be broken up accordingly by my conversion period. So this is the period per year. So now I need to make an adjustment when I'm going through and thinking about how my interest is being formed, because again, this formula that we just found is for compounded annually. And so what I'm going to do now is look at a situation where my interest rate is now I is equal to R over M for a certain principal P over a number of T years. And so let's break it down in terms of the period. So let's say for the first period, my A1 would be equal to my principal times 1 plus I, that interest that we just calculated, and that would be it. All right, now what about though if I want to go and do the second period? Well, the second period again is taking that money that we just earned in the first and multiplying it by another 1 plus I. Well, if I use what we just found previously, A1 is P times 1 plus I. So I would have P times 1 plus I times 1 plus I, which tells me that A2 would be P times 1 plus I squared. Something similar from before. If I follow this and do the third period, compound interest tells me that this is going to take the interest that we made and the money we made in A2 and multiply this by 1 plus I. Well, A2 was P times 1 plus I squared. Well, I'm going to multiply this by an extra 1 plus I. And so I get after the third period, the amount of money that's accumulated is P times 1 plus I to the third power. Now, if I continue this all the way to the nth period, so the nth calculation, then AN, so however much money I'm going to accumulate by that period, would be equal to the previous amount times another copy of 1 plus I. Well, how much is this previous account? Well, this previous account would be my principal times 1 plus I to the n minus 1 times, right? Whatever this number is the power that's being raised, right? First period, first power. Second period, second power. Third period, third power, etc. All right, well, I would multiply this a n minus 1 times an extra copy of 1 plus I. And so by multiplying 1 plus i's together, it's going to add 1 to the power, and I find that the accumulated interest would be P, or accumulated amount would be principal times 1 plus I to the n, which again would be what our prediction would be if I'm going to the nth period. Now, where this gets a little bit tricky, and what's going to take us to our final definition and then final example for compound interest, is that n represents the number of times that we are calculating. Well, this is being measured essentially by a certain amount of times per year times the amount of years that we go. For example, if I was to do compound, if I wanted to compound quarterly, m would be equal to 4. And so if I was to go 1 year, this would mean 4 periods. If I was to go 2 years, this would be 8 periods, etc. So that n, being the number of periods, is my compound, let's see, make sure I use the right name, my conversion period, times the amount, however long we're doing this for. And so with this and how we've defined I, we have our definition for the compound interest formula. All right, our compound interest is the accumulated amount is calculated by taking my principal, so whatever my initial deposit is, multiplying that by 1 plus my special interest, which is my interest rate divided by the number of conversion periods per year. And this is raised to a power of that number of conversion periods per year times the term, which is the number of years that we're going to do this account. And to practice using this formula, let's take a look at this example here. So example 1, find the accumulated amount after 3 years if $1,000 is invested at 8% per year, and then if that is compounded annually, semi-annually, quarterly, monthly, and daily. So what we should see is that as we increase the number of times that we compound, we should see more money in our bank account at the end of the same term because we're getting more interest on interest the more times that we compound, right? The more conversion periods that there are. So at this point, if you want to work through this problem on your own, go ahead and hit pause. I'm going to pause for a second and then go through and write out the work for this problem. Okay, so in our question, the very first thing that I want to go through and do is that for just the general information, I know that the principal amount in this problem is 1,000. I know that the interest is 8%, so the number I'm going to use for that is 0.08. I know that my time is 3, and then my M depends on which part of the problem that we're looking at. So in A, if I'm compounding annually, this means my M is equal to 1 because I'm only going to have a conversion period of 1 time. And so according to my interest formula, compound interest formula, A is going to be equal to my principal times 1 plus R, which is 0.08, divided by M to the power of M times T. Plugging this into a calculator will give me then how much money we have earned. And I am going to plug this in and see what I get. It's taking just a little bit longer than I intended to. This comes out to be approximately $1,259.71. Now this is interesting because this is the same answer that we got before when we did this exact problem a second ago. So B. All right, what if I want to compound semi-annually? Well, semi means 2, so this means I want a conversion period of 2. So in my compound interest formula, the accumulated amount would be my principal, 1,000, times 1 plus 0.08. And I'm going to divide this by 2 because that interest rate will get divided equally between those two conversion times. But this means that for each year, I'm getting twice as many counts. So I'm going to do 2 times 3 in the power. This will be approximately, after using the calculator, $1,265.32. Notice the increase. By increasing the number of times I'm compounding by 1, we actually earn about $6 more than we would normally, which in the great scheme of things isn't a ton, but $6 is pretty good. We are making money, which is always a plus. All right, in C, we're compounding quarterly, so M is going to be equal to 4. So this means my formula, my accumulated amount will be A is equal to 1,000, 1 plus my rate, which is 0.08, split 4 ways. And this means now that for after 3 years, I'm going to get a total of 4 times 3 times that I'm actually going to be calculating, so roughly 12. And so this is going to be approximately $1,268.24. So again, increasing by roughly about $3 here. For D, if I compound monthly, this time M is going to be equal to 12. So following the formula and plugging and chugging, this time my interest rate would be divided by 12, which means I'm actually going to get 12 times 3 total multiplications, which would be worth 36. And if I use a calculator for this, I would get $1,270.24 about. And then for E, if I was to do this daily, we're going to use 365. So this would be A is equal to 1,000, 1 plus 0.08 divided by 365. And then this would be 365 times 3. And this comes out to be roughly $1,271.22. And so here's our example for compound interest. In the next section, we're going to look at some important terms financially that we may be concerned about. For example, if I know how much I want to accumulate, then how much should I put in initially, which is generally the question that we're more so trying to ask. Like you're just trying to save up for a certain item, like a house. So if you want to do an account, how much should you put in? We're also going to look at what's called the effective interest rate. You see this when it comes into APYs for credit cards, so annual percent yield and things like that, or average percent yield. And then we're also going to look at the present value, and that's where we'll end in terms of some of the applications. So the remaining sections, again, we'll look at some more finance applications, and hopefully will help you later on a little bit just in understanding some terms when it comes to credit cards and loans, um, mortgages, and things like that. Okay, now in this section, what we're going to look at is what's called effective rate of interest. And what this is talking about is when you look back at our work for compound interest. So for example, let me scroll back up. When we looked at our work here, notice that as our conversion period, as my compounding changes from annually to semi-annually to quarterly to monthly and daily, the amount of money that we're actually earning for interest isn't exactly 8%. We're actually earning a little bit more the more times we compound. And so it can be kind of misleading then when you're looking at certain paperwork because you would expect 8%, but again, it's not 8% in terms of what you're actually getting. And so we want a way to better compare interest rates and compare programs and financial situations and credit cards. And so we need to come up with a better interest rate, a semi-new interest rate to make comparisons easier. And so one way that we can actually do this, as you see in the title, is called the effective rate of interest. And what the effective rate is the simple interest rate that would produce the same accumulated amount in 1 year as the nominal or stated rate compounded m times a year. So to help kind of give a notation for this and to help you kind of see the notation for it, let's assume that R is the standard or the stated interest rate per year, which is compounded m times, and its corresponding effect rate, we're going to notate with an R EFF per year. Let's assume that there's an initial investment of P dollars. Then the accumulated amount after 1 year at a simple interest rate, which is the effective rate, I'm going to express this as A is equal to P 1 plus R EFF. And again, this is after 1 year. And so this would be my expression. Notice this is taken from the simple interest formula from earlier. The rate again would be the effective rate. Now, the accumulated amount after 1 year for compound interest, where I'm compounding m times a year, is given by the formula here. A is equal to P 1 plus R m to the m here. And if we're going through and trying to solve for the effective rate, notice that both of these equations here are both set equal to A. In other words, we want them again to produce the same accumulated amount. Then I can set these two equations equal to one another. So I'm going to go through and I'm going to say that the principal 1 plus the effective rate is equal to the principal times 1 plus the interest rate over conversion times the number of times it's being compounded. Again, it's conversion. And I want to go through and essentially solve for R here. Well, algebraically, the first thing I'm going to do is notice that if I divide P over, those P's will cancel. So essentially, the left-hand side is just 1 plus the effective rate is equal to parentheses 1 plus R over m to the m power. And again, if I'm solving for the effective rate, then we have our formula for the effective rate. It is parentheses 1 plus the interest rate, the annual interest rate, divided by its conversion m to the m power minus 1. So this is how we can calculate the effective interest rate and then better be able to compare the different programs that we have. So I've got 3 different examples to go through and look at and essentially using this formula. The first one is a lot of plugging and chugging, so get ready with your calculator. Find the effective rate of interest corresponding to a nominal rate of 8% per year, but that annual 8% is being compounded annually, semi-annually, quarterly, monthly, and daily. So go through and see if you can use this formula, go through and calculate the effective rate, and then I'll go through and show the work. Okay, so for A here, notice in the formula that all I really need is R and M. And so in this kind of case, my nominal rate is 8%, so that'll be 0.08 for each part here. The M is what's going to change because the M is how many times I'm compounding per year. So if I compound annually, then the effective rate can be calculated by doing parentheses 1 plus 0.08 divided by 1 to the first power minus 1. Well, notice this inside here is just going to be 1.08 minus 1, which is 0.08 or 8%. And this should make sense because if we're just compounding once per year, then that is my simple interest rate. And like we've compared before, the simple interest rate and compound is the same when we compound annually. What we're going to really see a difference in is when I increase the number of times I compound. For example, in B, if I'm going to compound semi-annually, so my R again is 8%, but my M this time will be 2. So my effective rate is going to be calculated by 1 plus 0.08 divided by 2 squared minus 1. And I'm going to go through and use a calculator for this to solve for the effective rate. I would encourage you to do so as well. I get an effective rate of approximately 0.0816 or 8.16%. So notice that the effective interest rate that we're actually earning if I compound semi-annually is 8, more than just 8%. So again, see how that's kind of misleading from the given information of the annual interest rate. And so let's look at C now. So again, R is 0.08. M this time would be 4. Then my effective rate can be calculated by 1 plus 0.08 divided by 4 to the 4th power minus 1. And I get this to be approximately 0.0824, which is 8.24% in terms of my actual effective rate here. For D, we're doing this monthly. So I need to move this stuff down. We'll talk about this stuff in a minute. So for D, my interest or my annual rate is 0.08, but this time we're compounding monthly. And so M is going to be 12. And so then my effective rate is going to be 1 plus 0.08 divided by 12 to the 12th power minus 1. And this comes out to be approximately 0.0830 or 8.3%. Again, notice like how much of a difference this is in terms of a percent when comparing back to the original percentage. And so again, this is giving you a better idea of which route would either earn you more money or you'd be paying more money, depending on what we're looking at. And so for the final E, R is 0.08 again, but M is going to be 365. Then the effective rate would be 1 plus 0.08 divided by 365 to the 365th power minus 1. This comes out to be approximately 0.0833 or 8.33%. Again, displaying its effective rate. So this is just an example again of kind of the power and the effective rate versus the annual interest rate that's generally given with compound interest. Now like when you're looking at a problem, the more times you're going to compound, then probably the better it's going to be. But if you've ever looked at credit cards, if you've ever looked at loans, they don't actually tell you how many times it's compounded very clearly in terms of the numbers. Instead, what they give you is what's called the annual percentage yield and the APY. And I just realized that wording there is inside the second example, so I apologize. That APY, which is right here, is the effective interest rate. And what you're finding, and there's a Congress passed this 1968 Truth in Lending Act that requires that the effective rate has to be given. So that way, when you're comparing credit cards, when you're comparing these APYs, you can choose the lowest value. So that way, you're not paying as much on how much is owed. And so, the other benefit to this is essentially the formula. So instead of having to go through and do the entire compound interest formula, if I know the effective interest rate, then I can actually calculate the accumulated amount by using the simple interest formula instead of having to do the R over M to the M times T, which just can involve some greater numbers. We can solve it a little bit easier using this formula here, which we'll do in one of the following examples. All right, and so I've got two more examples to kind of look at. The applied example 3. So this is kind of about the investment options. And the wording, again, is going to be a little bit different than what you're used to taking a look at. And so Jane has narrowed her investment options down to two different options. Purchase a CD that matures in 24 years and pays interest upon maturity at the rate of 5% per year, which is compounded daily, and assume 365 days in a year. Or purchase a zero coupon, so she's not going to earn any interest, but it will triple her investment in the same time period. So it's essentially, do you want interest over the course of a time period, or do you want a guaranteed, excuse me, or do you want a guaranteed triple? Because the triple sounds like a lot. So which option will optimize her investment? Which option would be the best? All right, so let's go through and figure out what option would be best for her. Now, we're going to go through and calculate 1 and 2 and just kind of see how much she would accumulate overall. Now, one of the interesting things about this problem, though, is that we don't really know the principal amount, so we're just going to let the principal be P. And then let's go through for option 1. We know that the time is 24 years. The annual rate is 5%, or 0.05. And it's compounded daily, so M is going to be 365. So then A, according to our compound interest formula, would be P 1 plus R over M to the M times T. So plugging in the numbers that we know, 1 plus R, which is 0.05 over 365, 365 times 24. And using a calculator, this would end up being P times roughly 3, excuse me, looking at the wrong part. There's roughly about 3.32. And so essentially what this is telling us is that at the end of the 24 years, we would get 3.32 times the principal amount would be our final, which is interesting because in option 2, we're told that the accumulated amount in the same time period of 24 years would just be 3 times however much she invested. So when comparing the two, it turns out that option 1 would be better because we'd end up making roughly about 30% more. Roughly about 30% more than we would if we took option 2. 10% more, I guess. All right, so let's look at applied example 4. So applied example 4 deals with IRAs. It's actually interesting if you've ever done or heard of acorns in terms of an investment for younger people or wanting to do stocks for not a lot of money. You can essentially put money into an individual retirement account, so something separate. This is what the IRA essentially stands for. And so her money is invested in a money market mutual fund that will pay interest on a daily basis. Over a 2-year period in which no deposits or withdrawals were made, her account grew from $4,500 to $4,792.61. Now, what this problem wants us to find is the effective rate. So I want to know, what is our effective for this account if she's earning interest over that period. And so what we're going to do is we have a formula for this. If you remember, the accumulated amount is equal to the principal times 1 plus the effective rate to the amount of time that we go through. Because if I know the effective rate, this would give me the same thing in terms of compound interest. So what I can do with this problem then is actually set it up. We know the accumulated amount, and we know the principal, and we know the time because it's 2 years. I can go through and solve for my effective rate. We actually don't even need to know the 365. All right, and so dividing by 4,500, we would get 1.06502. That's approximated, so I rounded that. I need to take the square root of both sides. So I get 1.031998. That's approximately 1 plus the effective rate. So subtracting 1 gives me the effective rate is 0.031998, which means the effective rate is roughly 3.2% per year. Okay, so now what I want to talk about is what's called present value. Present value is looking at the amount that we should deposit initially. So what should the principal be to achieve some kind of accumulated value, which is the future value for a deposit, for an investment, etc. So essentially, if we go back to our original compound interest formula, which is A is equal to P times 1 plus R over M to the MT, this has been solved for A. So essentially, if I know the initial investment, I know the rate, the compounding, etc., then I can find what's going to be in the account later. Well, what if I want to know what to start with? Essentially, I want to take this formula and I want to solve it for P. So as you could probably take a guess, I'm going to go through and divide by all of this junk here on both sides. And when I do that, this is going to give me P by itself. So I'm going to have P is equal to A over 1 plus R over M to the MT. Now, I can bring this stuff out of the denominator by making the power negative. And so this is going to make it a little bit nice and neater, except it's going to have a negative here, which is going to be the most important distinction, because now what I have is a present value formula, so that if I know how much I want to have in the accumulated account, and I know how to compound it and I know the interest, I can figure out what the present value is. So this is my present value for compound interest formula. So here's an example, 2 examples coming up to go through and try this. So example 5, how much money should be deposited in a bank, paying interest at the rate of 6% per year, compounded monthly, so that at the end of 3 years, the accumulated amount will be 20,000. Okay, well, for the solution, just listing out what I know, I'm trying to figure out what P is. I know A is 20,000. I know R is 0.06 for 6%. I know it's compounded monthly, so M will be 12. And I know T is 3 for years. So now I'm going to go through and plug this into my new present value formula. So P is going to be equal to 20,000. So 0, 0, 0. 1 plus 0.06 over 12 to the negative 12 times 3. And then I'm just going to use a calculator to go through and compute this. And when you use a calculator to compute this, this will give me the present value, which comes out to be approximately $16,713. So I need to deposit this amount if I want this amount at the end of 3 years. All right, example 6. So find the present value of $36,605.70, due in 5 years at an interest rate of 4% per year that is being compounded quarterly. So to solve and to answer this question, again, I want to know what is P. If A is 36,605.7, my time is 5, my rate is 0.04, and my M is quarterly, so 4, not 12. And then again, I'm just going to plug and chug. So P is equal to 36,605.7, 1 plus 0.04 divided by 4, to the negative 4 times 5. And when plugging this into the calculator and plugging and chugging, of course, you would get 30,000 is the necessary deposit to get you 36,605. And so this is present value, pretty straightforward, definitely a little bit easier and shorter, and I think quicker to get on the uptake of what to do here. All right, and so the next section, what we're going to look at is 2 important questions to kind of ask yourselves, especially when we talk about compound interest. So from what we've seen so far, and again, intuitively, what you've seen over the past couple of years of taking math classes and talking about compound interest is we know that as the accumulated, or as the number of times we compound becomes more and more frequent, the accumulated amount goes up, right? So the amount of money you would make compounding quarterly would be higher if I was to then compound, monthly. To get more money, instead of compounding monthly, I should compound daily. Well, how should I compound? What if I want to make more money than doing it daily? Well, what if I did it by the hour? Well, what if I then compound by this minute? What if I compound by the second? Right? As I essentially increase the number of times I want to compound, the more money we can essentially make. So that's our first observation, right? What happens to the accumulated amount over a fixed period of time if the interest is computed more and more frequently? Well, then there's a following kind of logical question, which is, okay, well, if I continue to increase this frequency, is there some kind of limit to how much money we can make? Because it doesn't feel like if I go more and more and more frequently that I will just get an infinite amount of money. Otherwise, we would all have an infinite amount of money in terms of compounding interest. So there doesn't need to be, but there has to be some kind of limit, some kind of ceiling, some kind of boundary to how much money we'll have in our account. And this is essentially answering and asking this question of, what is continuous compounding interest? Like, what if I was to compound continuously, which is faster than a nanosecond, faster than that, and faster than that, and faster than that. So if this frequency goes, essentially, if I let M go to infinity, if I let the number of times I compound increase without bound, is there a bound to the amount of accumulation that I would get increase without bound? All right, so what I'm going to do to kind of start with this is go back to the compound interest formula again. So my amount is equal to the principal times 1 plus R over M to the MT. So again, this is my accumulation. Now the idea here is that I want to let M go to infinity. Well, I'm essentially taking a limit then. And I'm saying, okay, what's the limit of A? What's the limit of this formula if I let M increase without bound, if I let M go to infinity? Now, a couple of things to really kind of notice here, and we highlighted a little bit when we talked about limits, and I'm going to highlight again here, is the variable in question is an M. And so when I'm looking at this problem, I have an M here and I have an M here. And because of this is multiplication, this P is just a number, it's just a scalar. So it's actually true that I can actually bring the P to the outside of this limit and really just focus on this parentheses with this MT here. And not only that, I can also use properties of these powers here and actually even break this up further by really focusing on just this limit here and then raising it to the t. Because remember that your properties of exponents, if I have a power raised to another power, to simplify this, we multiply the two. So this would be m times t. So all I'm doing is splitting them apart. And so to answer our question of like, what's the boundary, like what's the upper limit here, I need to solve this limit. And this limit is really, really familiar to one limit we've already looked at the very, very beginning of this lesson. And so at the beginning, I can't spell beginning. There we go. At the beginning of this whole thing, we saw that the limit as m goes to infinity for 1 plus 1 over m, this is equal to e, right? This defined the natural number. And so what I want you to notice is that this definition here is very, very, very similar. The problem is that this has an r, and I need it to be a 1 in order for this definition to work. Also, I'm forgetting there's an m there. And so that's why we're really close for this working. So what I'm going to do is essentially a substitution trick. And this is pretty sophisticated. So let me know if you have any questions or you want to know about it. Ultimately, it's the definition at the end here that really matters. But let's go through and I'll show you what that definition is. Essentially what I'm going to do is I'm going to let u be equal to m over r. And so essentially this implies that m is equal to u times r. And as m, actually we'll do about that in a minute. So I want to go through and do this substitution. So my limit then, where I have the limit as m goes to infinity of 1 plus r over m to the m. If I just focus on that inside of the brackets there, I'm going to make this substitution here for m. So I'm going to plug it in here, and I'm going to plug it in here. So this becomes the limit, but inside the parentheses, I'll have r over ur to the ur. And before I kind of continue, notice that the r's themselves will cancel. So this gives me a 1 over u. But also there's no more m. So in terms of this limit being m is approaching infinity, that's not what I have anymore. I have a u now in terms of the variable that we care for. Well, notice that from our substitution, like our definition, as m goes to infinity, what does u do? Well, as m gets bigger and bigger and bigger, u will just get bigger and bigger and bigger and bigger. So u will go to infinity. And so I'm going to write this on the bottom, replacing it in terms of my substitution. So then my limit that I'm actually trying to go through and find right now is the limit as u goes to infinity of 1 plus 1 over u to the ur. All right, well, again, this r is not really affecting my limit, so I'm going to focus just right here. And notice that this definition is the exact same as this one. Right, the limit as u goes to infinity, 1 plus 1 over u to the u. Limit as m goes to infinity, 1 plus 1 over m to the m. This is equal to e. It doesn't matter what your variable is, we're always going to get e out of this. So that means in terms of this limit here, this is e to the r. So this goes here. So after I do my substitution, we would get a is equal to p e to the r raised to the power of t, which to simplify is p e to the rt. This formula right here, PERT, is my continuous compound interest formula, and it's the formula that you're most familiar with, and this is how it's derived using calculus and using limits and kind of the application of that. And again, it just says that as m grows without bound, this entire parentheses in the general formula, this entire thing right here boils down to e to the r. If I let m just go and go and go and go, the multiplier just becomes e to that annual interest rate. And so I've got one problem to kind of look at and solve. And again, we're just going to use the basic formula. This is what you'll see mostly in the practice. And it's also going to start us off by comparing essentially basic compound interest daily and compare it to continuously. Okay, so in this problem here, t is equal to 3, p is equal to 1,000, r is 8% or 0.08. And for a, I want to compound it daily, so 365. So I would have the accumulated amount is equal to 1,000, 1 plus 0.08 divided by 365, raised to the 365 times 3. And this would come out to be approximately, I'm going to grab my calculator. This would be approximately 1271.22. Now in part B, it's going to ask me to compound it continuously. So I'm going to use my A is equal to PE to the RT formula. So A would be 1,000 E to the 0.08 times 3. And when I do this in a calculator, I would get my final amount as 1271.25. In other words, notice that compounding continuously versus compounding daily is very, very, very similar in terms of our answers, because already we're doing it every day of the year. And even if we were to go to every hour or every second, specifically, there's not much of a difference. So that's why in terms of applications, you don't see companies compound interest continuously. You see them listed at a max of 365. But in theoretical economics and theoretical finances, we talk about this idea of it increasing continuously and what that value may be, because there is a difference. And the greater the payment at the beginning, the greater that difference could ultimately be. Using smaller principles, you're not going to see much of a change because we have smaller amounts, which makes sense. And so this is the end of our application in exponential functions. Make sure to look in the highlighted problems for practice. And then in the next video, we'll look at logarithms, which will let us kind of solve for other pieces in this.